another guest speaker. Today we have Professor Jay Lin from University of Illinois, Chicago. So let me just introduce Professor Lin. Dr. Jay Lin is a professor in the Department of Civil Materials and Environmental Engineering at the University of Illinois, Chicago, and the Institute for Environmental Science and Policy at UIC. Her research focuses on transportation system sustainability in both passenger and goods transportation. Lin received her master's and PhD in civil and environmental engineering from UC Davis, and a bachelor's in structural engineering with minor in computer science from Tsinghua University, China. She was a postdoctoral fellow at Harvard University before joining UIC. And let's welcome Professor Lin.
Thank you for the introduction. So I'm very delighted to have this opportunity to introduce one of the ongoing projects my group is working on. So before I get started, I want to acknowledge one of my PhD students, Shi Chen, who's actually the main driver of this research, and all the analysis was conducted by him. And I'm here only to present his work. So before I get started, can everybody see the screen okay? It's in the slideshow mode?
Yes.
Yes, great. Okay, thank you. So as you can see that I highlighted this term called long-haul electric truck in the title of my talk. So the reason for that is I want to emphasize the fact that what we're talking about is about long-haul electric truck, as opposed to passenger EVs or urban delivery trucks. So these are trucks that are driving long distance across the country to deliver goods. So I think if we look at the literature, so the literature is predominantly focused on passenger EVs, like the charging infrastructure, siting of charging facilities and battery technologies and so on and so forth. But relatively little attention has been paid to e-trucks, especially long-haul e-trucks. So we're hoping that this study will really serve as one of the starting points to fill the gap, the literature gap. So, and I also want to, before I get started, I also want to acknowledge that this project is actually our very own ICT project. This is partially funded by the Illinois Center for Transportation. So I'm grateful for that. And so let's get started. So I'm sure everybody knows that transportation is a major contributor to greenhouse gas emissions and energy consumption, right? So as you can see that typically we say that transportation contributes to about 30% of the total greenhouse gas emissions across all the sectors. But what I want to highlight here is that for freight trucks, even though generally speaking, it only makes up about 5% of the traffic on road, but it actually are responsible for 24% of the emissions. And so that's very high, disproportional contribution. And that trend has been increasing since 1990 by 93%. So that's why we need to also pay attention to freight vehicles emissions and energy consumptions, and anything we could do to mitigate the greenhouse gas emissions and energy consumption from this sector of transportation will really help the sustainability of transportation. Another reason why especially my group is particularly interested in freight transportation or freight vehicles is because we have all experienced this in the past 3 years, especially during the pandemic. So we see that although the overall traffic, especially the commute traffic, has gone down. So if you look at this plot, which I borrowed from the CMAP, Chicago Metropolitan Agency for Planning. So this is a figure that shows at the beginning of the pandemic to September 28, 2022, and you see that the blue line represents the passenger traffic. So generally speaking, you know, it's going down or gradually going back to the pre-pandemic level. But if you look at the truck traffic, so either the combination truck or the single unit truck, especially the single unit truck, so the level has actually gone up during the pandemic and after the pandemic. The reason is because we use online shopping a lot, right? Especially during the pandemic. So we're so used to that. And now we're still not willing to go back to the pre-pandemic level. So we just click and order things online. And guess what? For the package to get to your doorstep, you know, there are trucks behind the scene to do the deliveries. So the truck traffic has really gone up in the overall traffic. So the traffic composition has changed. So we replaced the passenger vehicles with this bigger, heavier, and more polluting vehicles on road. So that really implies that there's worsening situation in terms of the total greenhouse gas emissions and energy consumption. And there's some studies that have shown that by converting to EVs, and it brings environmental benefits. For example, the Department of Energy shows that if we reduce the fossil fuel powered fleet to EVs, then we can really reduce the oil dependency by 30 to 60%, and the greenhouse gas emissions by 30 to 45%. And also EPA shows that if we convert the freight trucks to electric trucks, then we can actually eliminate emissions and provide the health benefits up to $485 billion in 2022 dollars. So no doubt that electrification of transportation can bring this type of environmental benefits. The question is, well, so specifically for long haul trucks, the electrification adoption has been going really slow compared to the passenger EVs, right? We're really at the very beginning of e-truck electrification, the truck electrification or the e-truck adoption. I think there are several reasons why it has been much slower than the passenger EV adoption. And this is my list of the major obstacles for e-truck, especially for long haul e-truck adoption. But this by no means is a exhaustive or complete list of obstacles. You may have other things, and later on, actually at the end, I will also mention some other things that we did not investigate in this study. So the four obstacles are, so the first one, obviously, as I mentioned before, most of the attentions, including policy attentions and incentives, are predominantly focused on passenger EVs or the urban scale, the urban delivery trucks, this light, medium-sized trucks. So we don't have enough policy incentives for long-haul e-truck adoption. And the second obstacle is obviously the lack of charging infrastructure to facilitate this long-haul e-truck operations. And the third obstacle is the high initial adoption cost for long-haul e-truck, because trucks are bigger size vehicles, and the e-trucks are even more costly than the diesel trucks because of the battery costs and the necessary technological conversion of the vehicle technologies, right? So the initial cost is very high. And the last obstacle is the long battery charging time. As we know, even passenger EVs will take a longer charging time than just refueling your gasoline vehicles. And for trucks, especially long haul trucks, we're talking about much bigger battery sizes, and so the charging time is much longer. We're talking about at least 15 minutes to several hours of charging time for the e-truck battery to fully charged, right? So I'm going to talk a little bit about each of these briefly in the next few slides, and then we're going to move on to how we're going to tackle some of these obstacles. the first one, insufficient policy incentives, right? So as I mentioned, we know that the Biden administration has provided this $5 billion funding to EV charging infrastructure nationwide, which is the welcoming first step towards electrification. However, keep in mind that most of this program or this policy incentive is going towards the light and medium duty vehicles, not so much about the heavy duty vehicles. So that's why I consider this is insufficient policy incentives for long haul e-truck adoption. And if you look at nationwide, state by state, so this plot shows only a handful of states across the country really have what's called the zero emission vehicle or the low emission vehicle programs. Obviously, California is leading all the efforts in this regard, but you see that really only a handful of them have some sort of zero emission vehicle program or the low emission vehicle programs. And especially if you look at this table, so only the listed states here have some sort of electrification incentive program, financial incentive program to to provide funding for converting light duty vehicles or heavy duty vehicles and medium duty vehicles purchase or conversion. So that not a lot of states that actually have even the incentive programs for EV adoption, EV conversion and purchase. And the second obstacle, as I mentioned, the charging infrastructure, right? So this is actually the map showing the FHWA EV corridor at the current state, right? So if you look at the green lines, solid lines represents what's called the EV ready corridors. So meaning if you drive on these corridors, so there are what's considered sufficient charging infrastructure to facilitate the journey. But the dotted lines, the brown dotted lines are the ones that are in planning, but they're not ready, right? So then you can see that really the green lines are really, fine in between. So say if you want to go from West Coast to East Coast, there's no way you can go, through this highway system because, they're not connected. Or if you go from, say, Chicago, where I am, to, say, Florida, so there's no way you can drive a e-truck to go between the two places. So there's insufficient charging infrastructure for long-haul e-trucks. And I also want to point out that for this corridor to be designated as EV-ready corridor, so there are certain criteria applied by the FHWA. For example, I just want to highlight some of them. The spacing between the charging stations must be within 50 miles, and the charging stations must be placed within 1 mile distance from the interstate highway. And we're talking about all the fast charging, the DC fast charging the infrastructure. We're not talking about level 1 or level 2 infrastructure. So this is, and so what that means is the charging rate must be at least 150 kilowatt charging rate, right? So the third obstacle, the high adoption cost. So this is a study by the California Air Resource Board, CARB, and they show that for the whole statewide California state, if we have this kind of adoption scenarios over time from 2024 to 2035, so this shows the cost. So when it's negative, so if you look at this solid black line, so this shows the net cost or benefit. If it's negative value, it means cost. And if it's positive value, it's benefit, right? So you see that initially it's going to incur cost. And then in the long run, so hopefully this will, as the technology became cheaper and so on, so it will incur benefits. But the initial cost is negative, so it's initial negative cost, so meaning the initial adoption cost is high. Okay, so that's another obstacle that the industry is facing and the government is also facing. The last one, as I mentioned, the charging time. So obviously, so for each truck, the battery size is large. And from the carrier and the driver's point of view, the charging time, just like the break time and rest time, so it's unpaid for drivers. So that's one of the reasons they're not willing to use e-truck, because if you have long charging time, it's unpaid time. So why should I use e-truck, right? And in addition, I also want to point out this very important regulation, which we're going to incorporate in our analysis later on. All the truck drivers must follow this hours of service (HOS) regulation for the on-duty time, the cumulative driving time, break time, and rest time. So after certain hours, you must take a break or rest. So for safety reasons, right? So all these are disincentives for truck drivers or the carriers to adopt e-truck. So then for us, so we have a number of research questions we like to answer. For example, where to deploy these charging stations along the highways, right? So it's an indirect response to the lack of charging infrastructure question. And then when to charge. So the idea here is that because of this long charging time, and it's unpaid from the driver's point of view, so we want to minimize the impact of this charging time as much as possible on the total journey time. So if you have to spend too much time on charging, then it will really become very incentivized for the drivers. And so the idea is, well, so because the drivers must also follow this hours of service regulations, they must take time to rest or to break. So why not synchronize the charging time with the break time, the mandatory break time and rest time, right? So when the driver must take a break, the truck will be charged as well. So you don't have to, just to stop for charging, if you don't have to, because if you can charge when you're taking a break or you're resting. So that's the idea. So if we can actually minimize this impact, I think, and make a case, and I think the drivers and the carriers will be more willing to adopt e-trucks. And also, how many chargers to install at a charging station? That's one of the questions we like to answer in terms of the charging infrastructure. And also, we like to compare the e-truck with diesel truck to see, well, operationally speaking, is e-truck a viable alternative to diesel truck, so it can accomplish the same task in a similar ways, right? So in terms of the cost. So before I get into how we formulate the problem, how we answer those questions, I'd like to also point out that if you recall in the corridor, the EV-ready corridor designation, one of the criteria is to the charging stations must be placed within 1 mile of distance from the interstate highway systems. So obviously, right now we don't have a lot of this charging infrastructures along the highways. So, and to actually build such infrastructure is very costly. So our proposal is, why not build the infrastructure, the charging stations in the rest areas or the truck stops, the existing rest areas and truck stops. So as you all probably know, when you drive on the highways, there are these rest areas for people to pull over, to go to the restroom, take a break, stretch your legs, or even rest. The same thing for truck drivers. And there's also commercially run truck stops along the highways, or some of them are a little bit off the highways. If you can see from this map, so the blue triangles are the rest areas. They're pretty much along the highways, right, within 1 mile distance from the highway. And the green dots are the truck stops. Some of them are along the highways, and some of them are a little bit away from the highways. So our idea is, well, let's use this existing infrastructure and build the charging stations in these rest areas and truck stops. So this is a hypothetical study. Just to also keep in mind that currently this is prohibited by law to have any commercial activities at the rest areas. So these charging stations will be, if it's run privately, it would be considered commercial activities. So this is really a purely hypothetical study. However, I think at least from talking to IDOT project managers, and that there have been some talking about maybe changing the law to allow having this kind of activities at the rest areas. So let's hope that's the case. So if we further constrain the candidate rest areas and truck stops within 5 miles of the high voltage electricity transmission lines, because in order to build a charging infrastructure, you need to have this high voltage electricity transmission line. So if we say, well, we only consider the subset which are within this 5 miles of distance, then this is basically all the candidate rest areas and truck stops in the whole national highway network. So these are the candidate sites for the charging stations in our study. Okay, so how do we answer those questions? So basically, we build a mathematical model to optimize the electric routing and driver scheduling problem with coordinated charging schedules. So the idea is to figure out, well, minimizing the total truck routing cost subject to the hours of service regulation. And by doing so, we can figure out where to locate the charging stations along those candidate rest areas and truck stops, and how many chargers should be installed at each of these locations, and when to charge for the drivers, right? So that's the idea. And in this model, so the cost function, there are 6 cost components in this total cost function. So the one is the purchase cost, because we want to compare the e-truck with diesel truck. So we like to see if the high initial cost, what is the impact of the high e-truck cost, the purchase costs have impact on the total operating cost. So that's the purchase cost. And then we also consider the maintenance cost. In the e-truck case, that includes the battery replacement cost, because battery is very costly. So we take that into consideration. And obviously, we consider the driver's cost and the energy cost, which has 2 parts. One is when the vehicle is moving. So that's called the routing energy cost. And then when the vehicle is idling at rest or taking a break, because oftentimes the truck needs to have a heating or air conditioning and other things going on. So there's this auxiliary power unit going on, still running to consume energy. So that's the idling energy cost. And then lastly, we also consider, because each truck may have this potentially prolonged journey time due to long charging time. So there may be a late arrival for delivery. So there's a penalty associated with that late arrival at the customer locations. So these are the different components of the total operating cost considered in our model. And obviously, just like any models, we have a number of key assumptions. So the first one is this hours of service regulation, right? So this is the direct language from this regulation. So for example, the maximum cumulative driving time must be within 11 hours. The cumulative on-duty time maximum is 14 hours. And for each break, it's at least half an hour. And for each rest time is at least 10 hours. And we're talking about the consecutive operation days will be 7 or 8 days consecutively. And then after that, the driver has to take a break, from the duty. And the total cumulative driving time will be 60 to 70 hours within that 7 or 8 consecutive days. So these are the regulations. So the model has to take into consideration this regulations for the truck drivers. And another key assumption we assume is, as I mentioned, the charging stations are located at those candidate truck stops or rest areas along the highway. We don't consider any other locations for the charging stations. And we also assume each charging station has a charging capacity, meaning the number of charging slots. So there is a capacity limit. So if the demand is greater than the number of charging slots, then the trucks must wait for charging. And the state of charge of the battery must be maintained at all time at a certain level. So in this case, we use the literature finding typically 20% of the battery capacity is considered the lower bound of the state of charge. So the battery has to maintain at least 20% of the total battery capacity at any time. And this number 5 assumption is probably the most important one. So the idea here is to synchronize the schedule, the charging schedule and the routing schedule and the hours of service schedule for the drivers, right? So we want to take advantage of these hours of service regulation, the mandatory times for drivers, and then say, okay, if the driver must take a break for half an hour, at least half an hour, then the truck will also need to charge at that time. And so if the charging time is greater than half an hour, so be it. So that will be the total break time, because the half an hour is the minimum. And in the case if it's it's still within the hours of service time, but the state of charge is less than 20%, then the truck must charge and the driver must take a break or rest at the same time. And the last assumption, we assume that the battery is fully charged each time when the battery is being charged. So it's charged to full. Okay, so basically the general model's formulation is a route-based set partitioning problem. So if we consider a complete graph with a set of vertices and a set of arcs. So there are 3 types of vertices. One is we assume all the trucks start from a single depot. And there's also the customer locations, and as well as the charging stations, the rest areas, and the truck stops. And then we also define a set of feasible routes for any origin destination pairs, right? So so it will be a set of feasible routes connecting each OD pair on the network. So then the general formulation would be basically to minimize the total cost of all the possible routes on the network for all the OD pairs. And so that's the idea. So then to determine for each OD pair, the minimum total cost route would be formulated as such, right? So it would be the vehicle purchase and maintenance cost, the driver's cost, the energy cost, and the penalty cost. So this will be the vehicle cost, including purchase and maintenance, the driver's cost, the energy cost for moving energy and idling energy consumption, and the penalty cost. So I want to also point out that the 2 decision variables, the time for resting and time for break. So the rest time and the break time, the larger of the hours of service require the minimum time, and the necessary waiting time and charging time combined with quiet service time. So if the necessary waiting time and charging time is greater than the minimum break time, then the break time will be, the actual break time will be whatever is necessary for the charging and waiting in the model. So because we assume there is a charging capacity at each charging station, and so we basically have to model the waiting time if the demand is greater than the capacity, right? So we basically just use a very typical this MMC queuing model. So assuming Poisson arrival, departure with C is the number of chargers at a charging station, right? So we can walk through the probability of queue length and waiting time and so on mathematically. But I want to also mention that we did some numerical analysis to show that the total number of chargers is bounded by this ratio, right? Lambda divided by mu. So we decided to give a buffer, a little bit of buffer area to, so it would be lambda divided by mu plus 2. And then if we use this to to do some numerical empirical analysis, then it shows that the expected waiting time is this decreasing function of the number of chargers at a charging station, obviously. But interestingly, if the number of chargers is 6 or higher, then you see that the expected waiting time is drastically reduced from, this is in minutes. So from 50 minutes to like less than 10 minutes. But if you further increase the number of chargers at a charging station, for example, 8 or higher, then this reduction is really, really very minimum. So in other words, the number of chargers at a charging station would be probably, feasible between 6 and 8. If you want to have more than 8, the benefit of reducing the waiting time is really minimal. So there's probably no point in increasing the number of chargers, because that's also a cost associated with that. So in this study, later on, we actually fixed the number of chargers at each charging station at 6. And then obviously we also consider at the customer location, because we have the penalty if it's late. So we have to calculate the service time and arrival time and so on. So we give the penalty accordingly if it's early arrival or late arrival at the customer location. So in terms of the model constraints, so in the interest of time, I'm not going to go over each one of them, but we have 3 key sets of model constraints. The first one is obviously all the operations must conform to the hours of service regulations. And then the second set of key constraints are the synchronization of charging activities and with the rest and break activities. So the schedules must be synchronized. And the third set of constraints are the charging capacity, the battery capacity, and the state of charge constraints, right? So we say it has to be maintained at all time 20% and higher, right? And the initial will be obviously 100%. So we have to actually make sure that when it's getting to go below 20% in the next possible charging location, then the truck must charge at this current charging location. So that's the idea. So in terms of the solution method, so essentially this flow chart shows the step-by-step how to solve this problem. Essentially, there are 3 key steps. The first one is to generate a set of all feasible routes, this R set. And then for each of these feasible routes, then we calculate the total cost based on the cost function we defined earlier, and the model constraints to figure out the minimum cost routes for each OD pair. And then we do so for all the OD pairs, and then calculate the final total minimum cost for the entire network, right? So obviously there's some further constraints we consider in the solution method. So for the long haul routing, so we actually ignore the local routing, the detour portion of it. So we only consider the interstate highway portion from the beginning of the interstate highway to the end. So we don't consider the local detour routing portion of it. And also at the corridor level, so the origin destination pair on the interstate highway is given, right? So if you know the given corridor, the origin destination is given. And so basically the model is reduced to minimizing the shortest path, so to speak, the minimum total cost route. So then we apply this model to 4 case studies. So these are the 4 case studies in the order of the increasing distance. So the first one is on I-55 from St. Louis to Chicago. So that's just a little bit less than 300 miles. And then the second case study is from Chicago to Atlanta. So that's 758 miles of distance. And the third one is from Los Angeles to Denver. So that's a little bit over 1,000 miles. And then the last one is from coast to coast, from West Coast, Los Angeles, Long Beach to New York City port. So that's 2,838 miles of distance. So we look at these 4 case studies. So I want to point out that so for all these case studies, as you can see, these are all corridor studies. So meaning the origin destination are all given. So currently, she is working on extending this work to the entire national highway network system. So the true multiple origin destination pairs and the OD flows for the entire national highway network. And so this is the table that shows the key values for key parameters in the model. So I'm not going to go over all of them, but I did highlight some of them. For example, the charging rate for e-truck, we assume is 300 kilowatt. And remember, in the destination criteria, the charging rate is at least 150. So we double that rate. And this is considered not the highest charging rate available in the market, but it's a decent charging rate assumed. And the battery capacity, we assume it's 300 kilowatt hours. So again, it's not it's on the lower end of the battery size in the current market, but it's still a large battery size. And the number of chargers, as I mentioned, we set it to be 6. And the truck purchase cost. So for diesel truck, we assume the purchase cost is $160,000 per truck, per diesel truck. And we assume the lifetime mileage is 750,000 miles. And for the e-truck, we assume the purchase cost without the battery is $278,000. And the lifetime mileage is 300,000 miles. And for the battery, separately from the e-truck, is $72,000, and basically that translates into $240 per kilowatt hours. And the battery capacity, as I mentioned, is 300 kilowatt hours. That comes to be $72,000 for the battery cost itself. Okay, so these are the results of these 4 corridors we analyzed. So each one has we calculate for the diesel truck and for the e-truck, right? And then we compare the two. So the first column shows the total driving time for both the diesel truck and e-truck. And this B column is the brake time for both trucks. And the rest time. The total service time is basically the charging time plus the waiting time. The total journey time is basically the total driving time plus the break time plus the rest time, right? And then this F column is the percent service time, which is the total service time divided by the sum of the driving time and the total service time. And then this column shows the total cost and the energy used. So what you see is that obviously for each it incurs charging time, the total service time, right? So there's charging time and waiting time. So as a result, then there's a delay. So this shows the delay for the e-truck. So then the total journey time, as you can see, will be longer for the e-truck. So in this case, for the 4 corridors, we see that for the first one from St. Louis to Chicago, the difference. So the e-truck will incur more than 30% of the journey time, the total journey time. And then the good news is that this tend to reduce as the distance goes up. So when we go from the West Coast to the East Coast, so the prolonged total journey time is 16% of the diesel truck journey time. But if you look at the total cost, so it turns out that the e-truck is slightly higher. So based on the total cost function we define in the model, so the e-truck is slightly higher than the diesel truck, right? So at this point, it doesn't seem like, well, it's that big a deal. So it's slightly higher. But if you look at in terms of the energy use, there's a tremendous benefit from using e-truck. So there's very consistent over 70% of energy saving by using e-truck. But the point here is that you have this prolonged total journey time, right? So from anywhere between 16% to over 30% of the prolonged journey time compared to diesel truck. So what does that mean? We'll talk about that a little bit later on. And then if we look at the cost breakdown of each truck operation based on the table we showed in the previous slide. So for these 4 corridors, so these are the breakdowns. So the driver's wage is only about 25 to 28% of the total cost. Energy is 4%, very, very small. But for each truck, the big part is the vehicle purchase cost and the battery cost. You see that the two combined is over 60% of the total cost. So just these 2 items alone, the purchase and the battery cost, which is basically the e-truck cost alone, is 60% of the total cost. So if you compare with the diesel truck, this is the from this National Private Truck Council, the company produced this report, 2021 data. So the diesel truck purchase costs and maintenance costs is only about 27% of the total operating cost. And the driver range is actually the biggest part, which is over 55%. And in the e-truck case, it's only about 25 to 28%. So this is a very significant difference between the e-truck and the diesel truck. And so if we look at each of these corridors, so you can see that these are all these dots are the rest area or the truck stops, and the ones in red are the ones that are actually picked or chosen by the model as the charging stations, right? So there are 5 total rest areas and truck stops, and 2 of them will be selected as charging stations. The truck, in order to go through this corridor, must charge at these 2 locations. And if you look at from Chicago to Atlanta, again, certain stops or rest areas must be chosen as the charging stations. And the total charging stations required for this corridor is 7 out of 20 rest areas and truck stops along this corridor. And if you look at from LA to Denver, so there are a total of 30 rest areas and truck stops, and 11 of them are chosen as the charging stations. And then this already shown in the previous slide. So total driving time, charging time, and the induced delay is about 30% of the total driving time. And in fact, previously, it's also about 30% of the induced delay is about 30% of the total driving time in each of these cases. And the last one from LA to New York, total number of rest areas and truck stops in this corridor is 80 of them, and 28 of them are selected as charging stations. And the induced delay, again, is about 30% of the total driving time. So obviously, these results are subject to the values we pick for the parameters, right? So then we did some sensitivity analysis. So we look at first one is the total cost with respect to the e-truck purchase cost without the battery. Okay, so we consider the battery separately. So if we just focus on the blue line first, okay? So this blue line represents the estimated total cost by the model I presented earlier. And then this red dotted line is the diesel truck total cost estimated by the model. And this vertical line shows the default assumed model, the e-truck purchase cost, which is $278,000, right? And so obviously you can see that the e-truck has higher total cost than the diesel truck, obviously. But the break-even point is here when these 2 curves meet, right? So that means that this is about $200,000. So the e-truck without the battery cost has to go down to about $200,000 from the original $278,000 in order to have the similar total cost performance as diesel truck. Okay. However, because of the prolonged journey time, what that means is it represents the opportunity cost, because the prolonged journey time means, in order to provide a similar service, the carrier may have to have a larger fleet because the turnaround is slower because the longer journey time. and so on and so forth. So that's the cost imposed onto the carrier or the truck drivers. So that's called the opportunity cost. So if we factor in that opportunity cost due to the prolonged journey time, so the total cost by the e-truck is actually represented by this orange line. So then now the break-even point for e-truck to be cost competitive with the diesel truck, so the cost has to be around $81,000 or $82,000. So that's for the truck without the battery, and the battery, remember, is $72,000. So the two combined, it's a little bit over $150,000, which is actually just below the cost of diesel truck. So in other words, if we want the e-truck to be cost competitive, really the e-truck cost, purchase cost, has to be no more than the diesel truck cost in order for it to be cost competitive with diesel truck, which makes sense, right? And then if we look at the impact of battery cost on the total cost, so this is the e-truck battery, the total cost, and this is the model assume the battery cost, right? So you see that as the battery capacity, battery technology advances, and the cost is likely to go down. So we're going this way. But the interesting thing is, even if we reduce the battery cost to minimum, to zero, so it's still greater than the total cost of diesel truck. Okay, with assume the purchase cost in the model and so on. So in other words, even if we completely ignore the battery cost of each truck, it still costs more for each truck than the diesel truck. And obviously, if you look at the charging time in terms of battery capacity, in terms of charging rate, in terms of service rate, so as you can imagine, as the battery capacity increases, the total waiting time and charging time is decreased, right? And similarly, if the charging rate is going up and the service rate, which means the charging station capacity, is also going up in this direction, so the total charging time will be reduced, as imagined. And the point here is that this is a non-linear decreasing function. Okay, so then to summarize, basically, I hope I demonstrated to you that it's technologically feasible to deploy e-trucks for this long haul operations compared to diesel truck, because we showed that, well, with the existing infrastructure, we can locate those charging stations at the rest areas and truck stops, and at the minimum, we only need to convert less than 40% of them to meet the demand. And the benefit of it is over 70% of energy saving from e-truck operation. However, the study also shown there are great hurdles to overcome, right? The high initial adoption cost, the purchase cost of e-truck. So unless the cost has gone down significantly close to the diesel truck cost, that the cost remains to be higher for e-trucks. And also this prolonged journey time really means that, you know, in terms of the scheduling, in terms of the fleet turnaround, in terms of the the charging infrastructure, because it takes longer time for the fleet to turn around to meet the demand. So that means that the fleet size may have to increase, means more trucks have to be purchased. That means more trucks are deployed on the road. That means a lot more charging infrastructure is required, right? So these are all costs on top of the initial adoption cost. And other things we didn't consider are like, for example, the infrastructure cost, as I mentioned, and also a very important issue that we haven't really talked about in this country is the vehicle grid integration issue, right? So I think that's the end of my my talk, and I'll be happy to answer any questions.
Thank you, Professor Lin, for the nice presentation. We'll open for a couple of questions. If anyone wants to ask Professor Lin a question, we have a question on Zoom too. So I'll go ahead and ask Professor Ressler just as wouldn't the rest area create a large barrier to entry and operation, given it's run by government, agency, and bureaucracy? So we have some examples of rest areas that are closed for a couple of years. So would that be a barrier for this?
Well, we didn't really consider those issues. We just basically say, well, let's assume because these are existing infrastructures, and we can utilize this existing infrastructure to install charging stations. But obviously, I think each location may have its own unique situations and issues involved. But we didn't look into those issues. Yeah.
I have a question. Thank you for the nice presentation, Professor Lin. As you know, FHWA is also keen in getting to know more about inductive charging. I was just curious, in this framework, how do you integrate when there's a section that has inductive charging that maintains the discharge, and then how then the study changes on locations when you have sections of induction?
Very, very good question. Yes, we didn't really look at like different charging technology options, right? Personally, I'm not in favor of this inductive charging technology because the scalability is a huge issue. But we did not consider this, but I think in this case, you basically don't stop for charging, right? So I think in that case, then you still have the break time and the rest time as mandated, but the charging time will be just the travel time, right? So that will be a slight modification of the model. Yeah.
Yeah, it's very interesting presentation. One of the items that you mentioned is the constraints is the hours of service. And I've known a few truck drivers, and let's say they can be rather creative at bending those rules. And it just occurred to me that the handshaking that goes on with charging could be utilized, say, for enforcement of hours of service rules, and might one serve as a deterrent to adoption. But I was curious if you considered that the impacts of that at all.
That's an excellent question. One thing I didn't mention in my talk is that one of the implicit assumptions we made for the model is that we assume there's only one truck driver per truck. But we know that in practice that usually you have this the two drivers. They take turn to drive, right? So when one is driving, the other one rests. And then when the other one is rest, and then take over to drive. So then they don't have to stop. They don't have to stop to rest, right? So then they can minimize this rest time, because for the driver, any of this break time and rest time is unpaid time. So they want to minimize this time as much as possible. So oftentimes you see, if you talk to any truck drivers, oftentimes they have two drivers, either the father and son or co-workers. They take turn to drive. So then if you go back, if I can just go back to my slides. So when you see this big big number in here, this big number of rest time, 40 hours between LA to New York, it's really unrealistic. Drivers don't take this much time to rest, because they typically, for this, especially this coast to coast, you have two drivers take turn to drive. So we didn't consider that. We assume that it's only one driver. But you are right. So oftentimes the drivers bend the rule by doing all kinds of tricks. So we consider this is a more conservative case.
Okay,
Professor Lin, thanks for the interesting presentation.
Hi.
So just a quick clarifying question. You seem to assume that you know the route of the traffic, or is that endogenous, you think?
Very good question.
We have
So,
route choices.
yeah, very good observation. So as I mentioned here, all these 4 case studies are corridor analysis.
I see. Okay.
So we kind of simplified it because it's corridor, so we know the origin destination. So you can quickly determine, you know, which route is the shortest route, roughly speaking. And then we just on top of that, we consider the you know, because for long haul, typically you run on the interstate highways. You don't go on the local streets. You know, for the operation. So we kind of restrict this on only the interstate highway system. And so we kind of just predetermine the route for the corridor analysis. But as I mentioned, for the network level, you know, many to many OD pairs, then that becomes a different animal. So that's what my student is working on right now.
Okay, thank you.
Mm-hmm.
That ends our session for today. Thank you again, Professor, for the nice presentation. And thank you everyone.
Thank you.